Two things that sound like fantasy, and by the end of tonight, you'll see they're just plain physics. The first, I can take the exact quantum state of a particle here and hand it to a friend across the world, and the state itself never crosses the space between. It vanishes from my end and appears at hers, without travelling. The second, I can send that same friend a secret so well guarded that no computer ever built, not the ones we have, not the ones we fear, can crack it. Not hard to crack, cannot. And the astonishing part is that both fall out of one single rule, a rule about copying. So let me start there.
Start there, yes, because that one rule is the hinge the whole night swings on, and almost nobody outside the field has ever heard of it. It has a plain name, too. We call it no cloning. And I love that you put those two fantasies side by side, the teleport and the unbreakable code, because most people would never guess they're the same idea wearing two coats. They are, same rule. One time it's a curse, one time it's a gift. Shall we go and meet the rule?
Let's meet the rule, and start me where I'm comfortable, because copying is the most ordinary thing in the world to me. I copy things all day without a second thought.
You do, and that's exactly the intuition we have to take apart. Think about an ordinary bit, the classical kind, the atom of information from our very first night. A 0 or a 1. How hard is it to copy?
It's nothing. This whole conversation is being copied 1,000 times as we speak. Down a wire, onto a server, out to every listener. A bit gets duplicated so freely you never even picture it as an event.
For essentially nothing. And here's the thing to hold on to. You can copy a bit precisely because you're allowed to look at it. To copy a 1, you read it, you see 1, and you write another 1 next to it. The reading does the state no harm. You can read it 1,000,000 times and it just sits there, unchanged. Copying at bottom is look and rewrite.
Right, and a qubit, the quantum version, this is where it goes wrong.
It goes wrong at the very first step. Look and rewrite needs the look, and a qubit will not let you look. It isn't a hidden 0 or 1 waiting for a peak. It's a genuine blend, a direction it can point anywhere on that sphere we drew. Now, what happens the instant you measure it?
It collapses. That was the heartbreak from the start of the course. You go to look and the rich, full blend snaps down to a single answer. One bit falls out, and whatever subtlety was in there, the exact tilt of the thing, is gone. You broke it by looking.
You broke it by looking. So run the copying recipe and watch it die on contact. Step 1. Read the unknown qubit. But reading collapses it. You get one naked bit, say a 1, and the true state is destroyed in the act. So you write another 1 next to it. Congratulations, you have 2 1s. But the thing you were copying was never 1. It was some delicate blend, and you'll never know which, because the only glimpse the universe allowed erased the very thing you wanted.
So it's not that copying a qubit is difficult. The one move copying depends on, the look, is the exact move that wrecks what you're copying.
That is the whole of it. And you might think, all right, I won't be so clumsy. I'll build some gentle machine that duplicates the state without ever reading it. And the deep result, a genuine theorem, proven, airtight, is that no such machine can exist. Not we haven't built one. Cannot be built by anyone, ever. There is no device that takes in one unknown quantum state and puts out 2 of them. Full stop. That is the no cloning theorem.
Can you give me a feel for why it's impossible, though? It's a theorem, doesn't warm me. Where's the contradiction?
Here's the flavor without a scrap of maths. The rules that run a quantum system are at heart rules about smooth, even-handed rotation. And you can prove that a single fixed machine, which copies 2 different blends perfectly, would get tangled in its own logic. It can't respect both at once. The demand to copy everything faithfully is self-contradictory. So nature declines. It's simply not an available move.
And this is the rule you said was teased earlier, back when we were fixing errors.
The very same. When we did error correction, protecting a qubit you're not even allowed to read, no cloning was the shadow over the whole problem. It's why you couldn't just make 3 backup copies and vote, the way you would with a classical file. The universe forbids the backups. Tonight we look the rule full in the face. And the first thing to feel is that it seems like nothing but bad news. It ties both your hands.
It does feel like a pure loss. So let me make the loss concrete, because I think it sets up the whole puzzle. I've got a qubit in some unknown state. My friend across the world wants it, the actual state, faithfully. What are my options? Because it sounds like you've just closed every door.
Let's shut each one, because when they're all shut, you'll see why teleportation had to be so strange. Door 1. Just send the qubit itself. Put the particle in the post.
And the trouble with the post is these things are heartbreakingly fragile. The whole crisis a couple of episodes back. A qubit sent down a long fibre, jostled the entire way, arrives as mush. Decoherence eats it alive. Shipping the delicate thing across the planet is a losing game.
A losing game over any real distance. Door 2. Don't send the particle. Measure it, learn its state, phone the answer across, and let your friend rebuild it fresh. Just send the description.
Except that's door 1's problem again. To learn the state, I have to measure it, and measuring collapses it. I get one measly bit, not the true blend. I can never learn the state well enough to describe it. The description I'd phone across would be a lie, just whatever the collapse spat out.
Exactly. The universe rations you to 1 bit and keeps the rest. So the honest description doesn't exist to be sent. Door 3. Don't measure it, clone it, and fiddle with the copy until you've figured it out.
And door 3, we just nailed shut. No cloning. There is no copy to make.
So there you are. You cannot mail it, cannot measure and describe it, cannot copy it. Every sensible door is bolted. By every reasonable account, moving an unknown quantum state is simply impossible. And that's exactly the moment physics loves best. When it looks impossible, and then somebody finds the crack.
And I'm guessing the crack is the thing we spent a whole episode on and swore we'd use later. Entanglement.
The crack is entanglement. The strange resource from earlier. Remember how we framed it? Not spooky nonsense, not a secret telephone, but a genuine physical resource. A fuel the rest of the course would burn. Well, here's the fire. Tonight we burn some. Teleportation, moving a state that never travels.
So set the scene for me properly. Let me give our 2 friends names so I can keep them straight. Say it's Alice, who has the mystery qubit, and Bob, who wants it.
Perfect. Alice and Bob, the oldest couple in all of information science. Alice holds a qubit in some unknown state, and, crucially, she doesn't need to know what it is. Now the one thing they must arrange in advance, before Alice goes near the mystery. Ahead of time, Alice and Bob share an entangled pair, 1 particle each. Think of the pair we met before, the 2 coins, sealed and sent apart, that always land opposite. Alice keeps one, Bob carries the other to the far side of the planet.
So before anything interesting happens, they've each got 1/2 of a linked pair, a shared thread stretched between them.
A shared thread, the connection they'll ferry the state across. Now Alice does not measure the mystery qubit on its own. That only wrecks it. Instead, she brings the mystery qubit together with her half of the pair and measures them jointly. She asks one clever question. Not, what are you each, but, how do you 2 relate?
Let me make sure I've got that because it feels like the heart of it. She's not looking at either particle's value, she's looking at the relationship between them.
That's the heart of it. There's a special kind of joint measurement, a bell measurement, after the same bell whose insight into entanglement we leaned on before, and what it reads out is purely relational. It never asks, are you a 0 or a 1? It asks, are you the same or different, aligned or anti-aligned? It reads the link, not the values. And because it only touches the relationship, it never has to expose the mystery states blend, which is the only reason this works at all.
And that joint question hands back what to Alice?
2 classical bits. That's all, 4 possible answers, each just 2 ordinary bits she could write on a sticky note. And 3 things happen in that single instant. First, Alice's mystery qubit, in the act of measuring, is destroyed. Gone from her end, the joint measurement consumed it. Hold that thought, it saves us from a nightmare later. Second, at that very moment, Bob's faraway half of the pair changes. It leaps into a new state, and here's the wonderful part, it becomes the mystery state, the exact blend Alice's qubit used to have. It has crossed to Bob.
Wait, so it's already there. The instant she measures, Bob's got it.
This is the most important trap in the whole subject, so let me spring it before you fall in. Bob's particle becomes the mystery state, but scrambled. He's holding the right state in one of 4 disguises. It might be exactly as Alice had it, or flipped, or rotated, or both. 4 disguises matching the 4 answers Alice's measurement could give. And Bob has no idea which he's got. To him it looks like meaningless noise, useless.
So it's there, but locked, and the key to which disguise it's wearing is…
in Alice's hand. Those 2 classical bits. Her outcome tells her, and only her, exactly which disguise Bob is wearing. So the third thing. Alice picks up the phone or sends an ordinary email, a completely mundane classical channel, and sends Bob those 2 bits. And when Bob hears them, he knows which correction to apply. 2 bits, 4 disguises, 4 corrective moves. He does the one the message names, an unflip, an unrotate, or both, and the disguise falls away. Now Bob holds the mystery state. Exactly, perfectly, the real thing.
Okay, that's beautiful, and I need to slow it right down, because there are 2 claims flying past that I refuse to let you get away with. Claim 1. You said Bob's particle changed the very instant Alice measured, across the whole planet, instantly. That sounds exactly like the faster-than-light message you swore up and down was impossible. So which is it?
Good. This is the objection that separates people who understand teleportation from people who only think they do. Here's the answer, airtight. Yes, something on Bob's end shifts the moment Alice measures, but what does Bob actually have before her call arrives? A particle in one of 4 disguises, and he can't tell which. And if you can't tell which of 4 equally likely things you're holding pure noise. The finest instrument ever built gets nothing out of it but a coin flip. There is no information in Bob's hand yet. None. Genuinely, provably random.
So the state is there, in some bookkeeping sense. But there's nothing Bob can do with it. He can't read a thing off it.
Nothing. It's inert, and it stays inert until, and only until, those 2 classical bits arrive to tell him which disguise to peel off. And how do those 2 bits travel?
By the phone, the ordinary channel, which crawls along at the speed of light at best, same speed limit as everything else.
No exceptions, no cheating. So the useful state, the one Bob can actually possess and use, arrives no faster than that phone call, no faster than light. The instant leap on Bob's end is real, but it's locked, and the key travels the slow, lawful way. Entanglement did half the job, but it could never finish alone. It always needs those 2 classical bits to complete the crossing. That's why nothing here outruns light. The classical part isn't a detail, It's load-bearing.
That's the cleanest I've ever understood that. The entanglement is the pipe, but the two classical bits are the water, and the water moves at the ordinary speed. All right, claim 2, and this one I care about just as much. You called this teleportation, and my brain instantly went to Star Trek. A person dissolving here, reappearing there. And also, at the end, Bob has the state. Did we just copy it? Because you told me copying is flat out forbidden.
And this is where the first of my 3 things comes back to save us. The part I told you to hold. Remember what happened to Alice's original the instant she measured?
It was destroyed, gone from her end.
Gone. So count the copies at the finish. Bob has the state, Alice does not. 1 copy at the start, exactly 1 at the end. The state wasn't duplicated, it was moved. At no instant were there 2 of it. So no cloning is scrupulously respected. In fact, and this is gorgeous, teleportation only works because of no cloning. The destruction of the original isn't a side effect, it's mandatory. For the state to appear over there, it must vanish over here. Otherwise, you'd have 2, the forbidden thing.
So the disappearance isn't the price of teleportation. It practically is teleportation.
Beautifully put. And that's why teleport is the right word. Closer to the science fiction than you'd think, but with its logic tightened. In the stories, the transporter scans you and reassembles you elsewhere, and people ask the uneasy question, is the one who steps off the pad you, or a copy with the original quietly destroyed? Quantum teleportation answers with the force of a law. There is never a copy. The original must be destroyed for the far end to exist.
And to be crystal clear, no matter is traveling here. We are not beaming atoms across the world.
Not a speck of matter crosses that gap. Bob had his own particle all along, his half of the pair in his own lab the whole time. What crossed to it was the state, the pattern, the which way is it pointing. The particle is Bob's, only the quantum character was ferried over. It's the difference between mailing you my guitar and mailing you the song. Teleportation sends the song, your guitar plays it. And notice, this is the thread we've pulled since the first night. Information is physical. The state of that qubit is a real thing you can pick up here and set down there. Tonight you're watching us carry information across the world.
One more piece of the strangeness. The information that reached Bob. Where did it actually live during the trip? It's not in the 2 bits. 2 bits is almost nothing, 4 possibilities. A full quantum state has infinitely many shades, the whole surface of that sphere. You can't cram the sphere into 2 bits.
You've spotted the deepest thing in the whole procedure, and hardly anyone asks it. You're exactly right. The 2 classical bits cannot be carrying the state. There isn't room. So where was the rich part hiding? In the entanglement. The shared thread was preloaded with all that quantum subtlety, waiting before Alice touched the mystery. The 2 bits aren't the message, they're the instructions for unlocking what the entanglement already delivered. The entanglement carries the ocean. The 2 bits say which way is up. Neither alone tells you anything. Together, they move a world.
The entanglement carries the ocean. The classical bits say which way is up. That's the picture I'm keeping. So this has actually been done. It's not chalkboard fantasy.
Done and done again. Across tabletops, then down fibers between cities, then, most dramatically, up to a satellite orbiting overhead, teleporting the states of particles of light across distances that would have seemed absurd not long ago. Real, working, established physics. Now, we've just built a machine, and every good machine runs in reverse. Running this one backwards gives us a second little miracle for free. Superdense coding, the mirror image.
Run it backwards. Okay, teleportation was spend 1 shared entangled pair and 2 classical bits and you move 1 qubit. What's the mirror?
Listen to the shape of what you just said and guess before I tell you. Teleportation spends 2 classical bits to send 1 qubit's worth of quantum state. So the mirror should swap those roles. Spend 1 qubit to send 2 classical bits.
Send 2 classical bits by physically sending 1 qubit? That sounds like you're getting something for nothing. 1 particle carries 2 bits of message.
It does. No free lunch, but the bookkeeping is lovely. It's called superdense coding. Again, Alice and Bob share an entangled pair in advance, 1/2 each. Now Alice wants to send 2 classical bits, 1 of 4 messages. Depending on which she wants, she does 1 of 4 little operations to her own half. Flip, rotate, both, or leave it alone. Then she mails that single particle to Bob. 1 qubit, physically sent. And Bob now holds both halves, his own and the one Alice mailed, does a joint measurement across the 2, reads the relationship, and out pop 2 clean classical bits. 1 physical qubit delivered, 2 bits read out.
So the trick is the pair was already linked, and Alice's nudge to her half quietly rearranges the whole linked pair. And Bob, holding both ends, reads the rearrangement.
Exactly. The entanglement was laid down in advance as a prepaid channel. Count it honestly and there's no magic. 1 pre-shared pair plus 1 qubit sent equals 2 bits delivered. The universe won't let you smuggle information for free, but it will let you pre-position a resource and spend it cleverly later.
And I love the symmetry. Teleportation sends a qubit using entanglement plus 2 classical bits. Superdense sends 2 classical bits using entanglement plus 1 qubit. The same trade, read in opposite directions.
The same coin, both faces. Entanglement, classical bits, and qubits turn out to be currencies you can exchange at fixed rates. Once you see information as a physical stuff with an exchange rate, that's a genuinely new way to look at the world. Now, we've moved states, we've packed messages tight. Time for the gift I promised at the top. The moment the very rule that tied both our hands turns around and hands us something no one has ever had. An unbreakable code. Unbreakable codes, when eavesdropping is a law of physics.
Unbreakable. And you were careful with that word at the top. You didn't say hard to break, you said cannot. I want to hold you to that because I have a working idea of how codes go, and every code I know of is a race. The code makers get cleverer, the code breakers get cleverer, and today's unbreakable is tomorrow's cracked. What makes this one step off that treadmill entirely?
Then let me first show you the one classical code that genuinely is unbreakable. Because it's already known, it's over a century old, and understanding why it's perfect and why it's almost useless is the doorway to the whole quantum trick.
A perfect code that's useless? All right, I'm intrigued. Go.
It's called the one-time pad, and it's beautiful in its simplicity. Suppose Alice and Bob already share a secret key, a long string of completely random bits known only to them and, the crucial condition, as long as the message itself. Alice scrambles her message with the key, bit by bit. Bob unscrambles it with the same key. And here's the theorem, tracing straight back to the founder of this whole subject, Shannon, from our very first night. If the key is truly random, truly secret, and used only once, the scrambled message on the wire is perfectly meaningless to anyone without the key. Not hard to unscramble, provably impossible. An eavesdropper learns exactly nothing. The coded message is consistent with every possible message equally.
So that code really is off the treadmill. No amount of computing power touches it because there's nothing in the intercepted message to grab hold of.
Nothing whatsoever. The perfect cipher. So why isn't the whole world using it for everything?
I feel a catch coming.
The catch is the key. It has to be as long as the message, truly random, shared secretly in advance and never amused. So before Alice can send a single secret word, the two of them must already secretly share a mountain of random key. And how did that key get from Alice to Bob without an eavesdropper copying it on the way?
Oh, that's circular. To share a secret safely, you first have to safely share a secret. If I had a secure way to hand over the key, I could have just handed over the message that way.
You found the wound exactly. It's the key distribution problem, and it has haunted secret keeping forever. The perfect code has existed for a century, shackled to an impossible errand: getting the key across safely in the first place. And notice why it's so hard classically. A key is just bits. And bits, as we said at the top of tonight,
Can be copied freely and silently. An eavesdropper copies the whole key as it flies past, passes the original along so nobody notices, and now she has your perfect key and you're none the wiser. The copyability of bits is the exact thing that dooms you.
there it is. So what would you need to fix it? You'd need to send the key on something that can't be copied, where any attempt to look leaves a mark.
Oh, that's the no cloning rule, the curse from the beginning of the night. You send the key on qubits, because qubits can't be copied and can't be looked at without being disturbed.
You built it yourself. That's the whole idea of quantum key distribution, and the first full scheme was laid down in 1984. Everything that tortured us in the first half of tonight becomes a superpower the moment your goal is to catch a spy. Here's how they do it. Alice sends Bob a stream of single qubits. Think of them as individual particles of light, encoding the bit in something like their polarization, the direction they wiggle. And the one clever ingredient: for each qubit, Alice secretly picks not just a bit value, but at random one of two ways to encode it. In the first, she uses straight up and down versus side to side. In the second, the two diagonals, the tilted directions. Two incompatible codebooks. She flips a private coin for the codebook, another for the bit, and off it flies.
And the two codebooks are incompatible in the quantum sense we hit before. You can't cleanly read one with the other.
Precisely. Measure with the wrong codebook, and you don't just fail to read the value, you scramble it and disturb the state in the bargain. Now poor Bob is in a bind. To read each qubit he must pick a codebook, but Alice hasn't told him which she used. So for each one he flips his own coin, picks a codebook and measures.
So about half the time he happens to match Alice's codebook and reads correctly. The other half he picks wrong and gets garbage.
Exactly. And here's the step that makes it work. Charming, because it happens right out in the open. After everything's sent and measured, Alice and Bob get on an ordinary public line and compare, for each qubit, which codebook each of them used. Never the values, just straight, keep it, or straight, diagonal, throw it away. They keep only the matches.
And on the matches, their bits should agree perfectly. So now they share a string of secret bits. There's the key for the one-time pad. And it's secret because the only thing spoken aloud was the codebook choices, useless without the values.
That's it. So far so clever, but we haven't caught the spy yet, and that's the crown jewel. Put an eavesdropper on the line, Eve, and watch what physics does to her. In the classical world, she'd copy every bit and stay invisible. But now she's holding qubits. First curse, no cloning. Can she make a quiet copy, let the original sail on untouched, and study it later?
No, that's the forbidden move. She can't copy an unknown quantum state at all. The thing that made classical eavesdropping trivial simply isn't available to her.
Gone. So her only way to learn anything is to measure the qubits as they pass. But she faces Bob's exact dilemma. She doesn't know Alice's codebook, so she guesses, and half the time she guesses wrong. And when she measures with the wrong codebook,
She scrambles it. She doesn't just fail to learn that bit, She changes the qubit before it reaches Bob. She leaves a mark.
The whole game. She has to send something on to Bob, or he'll notice qubits going missing. So she sends her best guess. But now, on some qubits where Alice and Bob used matching codebooks and should have agreed perfectly, Bob gets the wrong answer, because Eve roughed it up in the middle. Errors appear that simply cannot be there if no one was listening.
So eavesdropping doesn't just risk exposure, it forces exposure. Listening physically injects errors into the key. And how do Alice and Bob check?
They sacrifice a handful. After sifting, they take a random sample of their shared bits and compare them openly. Spend them just for the check. If the sample agrees near enough, the line is clean and they trust the rest. But if there are errors above what ordinary noise explains, someone was listening. Eve's fingerprints. And they do the only safe thing: throw the whole key away and start over. She never got a usable key, and they know she tried.
So the security isn't resting on a hard maths problem that a clever enough computer could someday chew through. It's resting on the fact that measuring a quantum state disturbs it. It's resting on a law of physics.
On a law of physics. And that is the phrase to carry out the door. Every classical code in the world, the encryption guarding your bank, your messages, your secrets right now, rests at bottom on some mathematical problem being hard. Hard to factor a big number, hard to undo some scramble. And hard is a promise with an expiry date. Remember what we saw a few episodes ago, the factoring algorithm, the one that put every secret on the internet on a countdown clock. The day a big enough quantum computer runs it, those hard problems stop being hard, and that encryption falls open like a book.
Whereas this doesn't care how powerful your computer is. There's no sum to out-muscle.
None. You cannot compute your way past no cloning. You cannot out-process the fact that measurement disturbs. A quantum computer the size of a galaxy gets Eve exactly nowhere, because the thing standing in her way isn't a calculation. It's the structure of reality. That's why the word is unbreakable, and why I wouldn't let you soften it. Not unbreakable until someone's clever. Unbreakable because the universe itself audits the line, and any spy trips the alarm just by looking.
And it's the same rule. That's the thing that's landing on me now. No cloning tied both our hands in the first half of the night. We couldn't copy, couldn't peek, couldn't move a state the easy way. And it's the very same no cloning, the very same you can't look without disturbing, that now makes it physically impossible to spy on the key. The curse and the gift are one rule.
One rule, two coats. That's the whole shape of tonight, and you've closed your hand right around it. The universe forbids you from copying quantum information. That forbidding is a wall when you want to move information, and you climb it with teleportation, borrowing entanglement and two honest classical bits. And that exact same wall is a fortress when you want to protect information, because the spy can't climb it either. Same wall. Depends which side of it you're standing on. The quantum internet, the vision, honestly.
So we can teleport a state and we can share a key no one can steal. It feels like these want to grow up into something bigger, a network. Is that where this is heading? A quantum internet?
That's the horizon. And let me sketch it honestly, the promise and the hardness both, because we don't do hype on this show. The dream is a network whose links are made of shared entanglement. Any two nodes that share an entangled pair can teleport quantum states to each other and generate keys no eavesdropper can touch. Entanglement becomes the fundamental resource you distribute. You spend your nights laying down shared pairs between cities, the way we lay fiber now, and spend them by day to move states and secrets.
And immediately I hit a wall, using tonight's lesson against you. Our ordinary internet reaches across the world because we amplify the signal. Every so often a repeater reads the weakening signal and rebuilds it strong. But you've spent all night saying you can't read a qubit without destroying it and can't copy it. So you can't build one of those repeaters. Doesn't that cap how far this reaches?
You've just rediscovered the single biggest obstacle in the whole field from first principles. You're dead right. Read and rebuild is forbidden here by no cloning. A qubit sent down a fiber fades, and you may not amplify it the classical way. So the signal thins toward nothing, and naively, that dooms the quantum internet to short hops.
But you've got that look. There's a way around.
A beautiful way, and it uses tonight's own tools. Teleportation turned into a relay. It's called a quantum repeater. You don't push one fragile qubit the whole way. Instead, you establish entanglement across each short hop, short enough that it survives. And then, at each way station, a little joint measurement splices the short links into one long one. Stitch one linked to two, and two linked to three, into one linked to three directly, even though 1 and 3 never met. Teleportation, handing entanglement down the line, extending the thread hop by hop, without ever copying or reading the precious state.
So you never amplify, you extend the entanglement, splice by splice, then teleport across the finished long thread. You route around the no-copy rule by never needing to copy.
Exactly. The repeater doesn't rebuild a signal. It grows a connection. And that, in principle, unshackles the whole thing from distance. Now, the honest part. This is hard, genuinely, presently hard. Those little pairs are fragile. Everything we suffered through in the noise episode bites here too. Storing entanglement long enough to splice it, keeping it alive against a world constantly trying to measure it for you. Ferocious engineering problems, fought over right now at modest distances, a step at a time. The key-sharing half is further along, real, run city to city and up to satellites. The full teleporting, computer-linking quantum internet is early. A vision with real foundations under it, not a product you can buy.
But even the sober version is striking. What would we actually do with it?
A few things that genuinely need it. Link separate quantum computers into one larger machine so you network smaller ones instead of building one impossibly gigantic processor. Share provably secure keys across a continent, even send a problem to a distant quantum computer without revealing what you asked. Your question stays private even from the machine answering it. And tie distant instruments together, telescopes, clocks, with a precision shared entanglement can sharpen. All of it built on tonight's two moves. Move a state, share a secret, with nature's no-copy rule underwriting the safety of the whole thing. Close. One rule, two coats.
So let me try to gather the whole night into one breath, because it's rare that so much hangs off so little. We started with what looked like pure bad news. You cannot copy a quantum state, can't peek at it, can't clone it, can't back it up. And that one prohibition, which seemed to close every door,
turned out to be the key to two rooms nobody thought you could enter. Go on, say them.
Room 1, teleportation. Because you can't copy or mail or measure the state, you move it a stranger way. You pre-share an entangled pair, make one clever joint measurement, and send two ordinary classical bits. The entanglement carries the ocean. The two bits say which way is up, and it never breaks the light speed limit, because without those two slow classical bits, the far end is just noise. And it never copies anything, because the original has to vanish for the far end to exist. The books always balance to 1.
Room 1, exactly. And room 2?
Room 2, the unbreakable code. Because a spy can't copy a qubit and can't measure it without disturbing it, any eavesdropper on your key is forced to leave fingerprints, errors that physics itself puts there the instant she listens. So you can share a secret key whose safety rests not on some sum being hard, but on the laws of nature. And the same no cloning rule that was the wall in room 1 is the fortress in room 2. One rule, two codes.
One rule, two codes. And here's the note I want to leave ringing. None of tonight was magic. That's the thing I most want you to walk away holding. Every single piece of it fell straight out of things we'd already earned together, earlier in this very course. Entanglement, the strange resource. We spent a whole night on it, and tonight we finally burned some. Measurement disturbs the state. We learned that heartbreak long ago. Tonight it became a burglar alarm. Information is physical, the thread from our very first conversation, and tonight we literally picked information up in one place and set it down in another. Nothing new was smuggled in. We just took the rules we already believed and followed them all the way to their beautiful, slightly outrageous conclusions.
That's the part that stays with me. Teleportation and Unbreakable Codes sound like two different science fiction movies, and they're the same 3 or 4 facts about qubits, honestly followed to the end.
Honestly followed to the end. That's all physics ever is, on its best days. And it leaves us right on the doorstep of the next question, which we've been quietly dodging all night. Every single thing tonight assumed we actually have these qubits, real ones that we can make and hold still and entangle and measure on command. And that is monstrously hard. So next time, we go and look at the machine itself. Not the ideas, the thing. The actual object, sitting in a lab, colder than deep space, where all of this either happens or falls apart. We go and see what a quantum computer really, physically, is.
The song, and finally the guitar. I'll be there. Good night.
Good night.